So now we're going to do page 407, number 18. So you're just given two equations, 4 minus x squared, 2 minus x. You can look at the problem if you want, but all the important information is here. So you're not given, y equals 0, x equals 0, the x-axis, the y-axis, anything of that. You just have these two curves, and these two curves are going to enclose a region, and then we're rotating about the x-axis. So first, try on your own, see if you can draw this. See if you draw what you think that looks like. Here's my drawing of the functions, but I haven't rotated it yet. So I guess I'll go through and sort of show how I'm going to do that. So I'm gonna in order to rotate it. So first of all, maybe look at the fact that this is your region in here. So now, what's going to happen when I rotate it is there's going to be an empty space in it. So that's what we're going to call a compound region. That's sort of my made up name for it. To distinguish it from the simple regions that don't have holes, because the equation sort of changes. So I'm going to create my mirror image, but just of the part of the parabola that we're actually going to use, which is right up to about here, sort of like that-ish. All right, and then we have this. All right, so that's my reflection. It's sort of like a highly exuberant Pac-Man. But remember that it's not a 2D Pac-Man. This thing is a solid rotated thing, so we're rotating it around like this. So it has like this open, this is an open end here, and then like the outside of it is rotated all the way around. So it's like a bowl shape on the outside. This is where they get sort of hard to visualize. The outside is this sort of bowl shape, okay? But inside it's got a hole that is conical, all right? So it's like this solid bowl shape that has a conical hole in it that comes down to a pinpoint, and technically I guess you could say it goes through, but only at exactly one point. You can pass through an opening at the end of diameter 0. Yeah, so but that's what it is. It's this sort of round bowl with a conical cutout. So imagine I take a big, this round thing, and then I drill a cone out of it. That's what you got there. Okay, now, how am I going to find the volume of that? Well, what you're going to look at our ith area element in the 2D region. So if we look at our 2D region, here's the ith area element, right? That's a sub I in the 2D world. So when I rotate that, what kind of shape am I going to get? When I rotate just that a sub I, rotate that around the x-axis, what am I going to get? So I'm going to try rotating just the back of it. Maybe it'll be a little clearer, because it's going to form this. It's going to form a washer, but the washer is going to have a hole in it, right? So that's just like the back half of that. So if I pull out this ith volume element, all right, what it actually looks like is a washer. So it's actually a disc with a hole in it. We usually call it a washer. So you'll hear all your calculus people calling this a washer. You can't actually wash anything with it. It is like if you went to the hardware store and asked for a washer, they would give you one of these. I have no idea why it's called a washer. Sort of an interesting, now I'm going to be thinking about that all night. All right, but that's what it's called. It's called a washer. If there's no hole, it's called a disc. If there's a hole, it's called a washer. All right, so now what we need to know is, what is the volume of the washer? All right, so the volume, what we're going to do is we're going to decide that there is an outer radius, a big radius, which will denote capital R, and then there's a smaller inner radius, which we'll denote with lowercase r. Then the volume is essentially the big cylinder minus the little cylinder, right? So it's going to be pi big R squared h minus pi little r squared h. And then we'll just, we can factor out the pi and the h, but then for some weird reason we're going to put the pi on the left and the h on the right. So that's our volume formula in general, volume for a shape of this nature. So for our particular v sub I that we have, our v sub I, we're going to have pi. All right, now let's think what r and what big R and little r are. What big R and little r are. R? Already R. All right, we got pirates teaching you calculus now. R. So where are these radii on this diagram? Well, the big radius is the 4 minus x squared. It's the outer function. The little radius is the inner function, which is 2 minus x. So if we wanted to talk about those generally, we could have the outer function, we'll call it something like g of x. squared. And then the inner function is going to be f of x squared. And then what's the height? Well, the height every time is the same. It's delta x, unless you're integrating with respect to y, and then it's delta y. But it's delta something. All right, so this is sort of the general idea of this equation. And so you want to think this is like top minus bottom function, although it's going to start being useful to think that it's outer minus inner. If you can always think it's the larger number minus the smaller number, because we have to have positive volume. So we're going to do a large number minus a small number. Then we can turn this into an integral by taking the limit of our v sub i's, take our limit as n approaches infinity of our v sub i's, and we're going to end up with a general equation for shapes of this nature, which is v equals pi times the integral from a to b of g of x squared minus f of x squared dx. By the way, technically these x's should have i's. They're x sub i's. So it doesn't matter. It's going to come out in the washer, so to speak. So there's your equation for integrating something like this. And then we also need to, we're integrating with respect to x, so we need to know that the limits are x coordinates, so we need to find out what they are. So these limits are x coordinates because we're integrating with respect to x. All right, so we might need to solve for them. So in order to do that, we're going to solve, I guess I'll put this over here. Put this over here. We'll solve to get our limits. 4 minus x squared equals 2 minus x. So you're going to get x squared minus x minus 2 equals 0. X minus 2, x plus 1 equals 0. X equals 2, x equals negative 1. Those are going to be our limits of integration. By the way, I wanted to make a comparison with this. Like, if you think about the 2D version, all right, in the 2D version, think, how would I find the area of this, just the area of the flat part, right, of that region? You would do area is equal to the integral from a to b of g of x minus f of x dx, right? That's the 2D version. So this is the 3D version, right? So this equation is a version of this formula that creates a 3D effect by rotating around the x-axis. All right, so now what I have is my volume is equal to pi times the integral from -1 to 2 of 4 minus x squared minus 2 minus x squared, because that's my g of x, my f of x dx. And all I have to do is do that integral. You should try to do that integral now by hand, and I will present the solution in the next video.